Okay, okay. We are about 40 people, so let's start. Hello, everybody. Today we have a great pleasure to listen to the lecture by Rajesh Gopakumar, who will tell us from some lecture. The title is From Fields to Strings and Back. Please, 1 hour.
Thank you very much, Irina. And it's a pleasure to join you all virtually. I will try to, my original title was Deriving Gauge-String Duality, which is really the message of my talk, but I thought I would frame it in a little more general way, about from fields to strings and back, because it is really about the relation between quantum field theories, and which we all know and understand, and string theory, which is perhaps a little more unfamiliar, little more something that many people are sometimes very skeptical about, and it seems like a very speculative thing. But I'll try to make the case that fields and strings have a very tight connection, and which actually goes back, has a long history. So, oops, let's see. Okay, so so this is roughly the plan of the talk. I will first say a little bit about this thing that's called the gauge-string duality, or sometimes the ADS-CFT correspondence, and why it is important, a little bit more at a very general level. And then I will try to sketch a program which I have been pursuing for a long time to understand this organic relation between gauge theories and string theories, or from the point of view of, or from a certain point of view of going from a world line picture to a world sheet picture. So this will be framed, or rather in recent years, some of the work which has kind of, I think, given evidence for this, that this program can be carried out, has happened from the ADS-CFT correspondence, which I will describe a bit, but in a special limit called the tensionless limit, where I will try to say how one can try to go precisely, in little more precisely in that case, how to go from fields to strings, and in some cases kind of close the circle, and that's the back in my title, from strings to fields, and maybe end with a very quick outlook. Since I think there might be some students, or this will be, first part is sort of very general remarks, not for the experts, of course, but this is to say that we know in 20th century theoretical physics has had two big pillars, quantum field theory and general relativity, which are more theoretical frameworks, and which between them describe the better part of our universe, from the smallest length scales to the largest length scales. And in particular, the framework of quantum field theory is a very powerful, very versatile framework, which we know now describes all non-gravitational forces at the quantum level. In fact, a class of quantum field theories, namely the Yang-Mills gauge theories, seem to capture most of the all the non-gravitational forces we know, the electroweak and the strong interactions. But quantum field theory is actually even more general, and that's why it's powerful, because it captures complex phenomena and phases of nature in statistical physics, condensed matter physics, fluid dynamics, etc. While general relativity, we all know, is a classical theory, and it describes gravity via the dynamics of space-time geometry, and of course that's the best description we have of the very large-scale universe, but it holds remarkably well almost all the way until the Big Bang. So these are, of course, the two big characters. These are experimentally well tested. As I said, they are the pillars of 20th century physics. And just string theory, very crudely in one slide, I mean, at least to begin with, what is it? It's in some sense, it is also a framework. It is an ambitious framework which tries to generalize quantum field theory so as to also incorporate gravitational interactions at the quantum level. And this exploits an observation many made it almost maybe 40, 50 years ago now, that a closed string, like a rubber band, like closed string without any boundaries, that contains the graviton as one of the lowest modes of excitation. And you can consider the interactions of strings by very similar rules like those of Feynman diagrams. So you can kind of draw the analogs of Feynman diagrams for the interactions of strings. Now they are given, instead of whirl lines like in the Feynman diagram, you have these whirl sheets as the string traces out a trajectory in time. So here I've drawn time on the vertical axis and space. So you can think of this as two strings colliding and two strings emerging. So you have Feynman diagrams and you have analogous stringy Feynman diagrams. And the quite surprising fact is that this gives already a finite, consistent description of quantum corrections to Einstein's equations, which is not very easy to otherwise achieve. So that was the initial reason why people felt there was some promise in string theory. But let me just continue with that a bit. So what is the rule here in string theory? It is the same like in Feynman diagram expansion in a quantum field theory, like we learned. You can, when you consider the string coupling to be small, and the string coupling is essentially playing the role of Newton's constant, which we know is in some sense small for low energies. So the string coupling constant is weights the genus or the topology of the Feynman diagram. So Feynman diagrams which have many holes in them, or these kind of donut-like holes in them, they are suppressed by higher and higher powers of this coupling. So this the whirl sheets are Riemann surfaces, two-dimensional surfaces. They are classified by their topology, which means or their Euler number. And the genus in particular is very simply related to the Euler number. And you have suppression for diagrams of higher genus. That's the same as the usual Feynman diagram suppression of higher loops in a perturbative expansion. So, okay, so that is just one slide, quick thing on string theory. We will come back to elements later. What was, I think, the main message of my talk, or the main, not the message, the main kind of the context of my talk is what is often called gauge-string duality, which is completely unexpected when it was proposed, equivalence between string theories, that is theories of quantum gravity on a class of spacetimes, and gauge theories on their boundary. So the class of spacetimes are these anti de Sitter or hyperbolic spacetimes, and you can consider them in Lorentzian or Euclidean signature. In the Lorentzian signature, it's often represented by this tin can-like picture with the time and the vertical axis, and you can think of the cross sections as spaces of constant negative curvature, and the whole space-time has constant negative curvature. These are the anti-de Sitter spacetimes, or little more generally, you can consider asymptotically anti-de Sitter spacetimes. And the corresponding, this equivalence is between string theories or quantum gravity theories in this class of spacetimes, and another set of, and and a set of quantum field theories, which are regular quantum field theories without any gravity. And for the case of asymptotically anti de Sitter spacetimes, the quantum field theories are conformal or asymptotically conformal field theories, or CFTs for short. And this is why the ADS CFT kind of thing comes up. So these quantum field theories are actually gauge theories. And in fact, in the large N limit of gauge theories can be organized by their rank, the SUN gauge theories. For instance, if you consider that family and take specific large N limit, a la Toft, then the statement is that at least for a class of such quantum field theories in the large N limit, which are asymptotically conformal field theories, there is an equivalence to the string theories or gravity theories in anti-de Sitter spacetimes, asymptotically anti-de Sitter spacetime. What is very remarkable about this correspondence, and I think even though it's now about 25 years old, it is still, at least it doesn't fail to amaze me, that how it can translate questions in quantum field theory to questions in string theory or gravity. And this happens via a kind of a holographic dictionary between the bulk, so to say, of the theory, this anti-de Sitter spacetime, which is a d+1 dimensional spacetime. And I forgot to mention, or I forgot to emphasize, that the quantum field theory can be viewed as living on the conformal boundary, which is a d-dimensional spacetime, if you wish, the boundary of this tin can. Here you see I have like a water bottle here, the boundary of this water bottle. That's a d-dimensional theory, and you can consider non-gravitational conformal field theory living on that, or an asymptotically conformal field theory living on that. And the claim is that there is a dictionary, and it's holographic because it kind of relates observables in d dimensions to those in d+1 dimensions. But this is not just some formal statement. It is actually a very useful statement. That's why it's called a duality, because it actually relates regimes which are accessible in one side to inaccessible regimes on the other side. Thus, for instance, if you want to study the quantum field theory when it is strongly coupled, strongly interacting, which is outside the domain of perturbation theory, then it translates, in this case, at least in the large N limit, to a weakly curved ADS. So an anti-de Sitter spacetime which has a very small curvature or a very large radius. And that is something you can access by even studying Einstein's equations, so classical Einstein's equations. So you're trading off, you're kind of relating quantities to compute in a strongly interacting quantum field theory to some classical computations on a weakly curved anti-de Sitter spacetime using Einstein's equations. And so there you are going from this inaccessible area in the quantum field theory to an accessible one in the gauge theory, in the gravity side. Vice versa, you can look at an accessible region in the quantum field theory, namely when it's weakly coupled, and where you then just use the rules of perturbative quantum field theory that you learn in your quantum field theory course. That regime, which is very sort of vanilla regime, translates to something which is very highly curved in the anti-de Sitter spacetime, where the radius of curvature is very small, or the curvatures themselves, the curvature invariants are very large. So, and that's something which is well outside the domain of Einstein's equations, classical gravity, classical Einstein gravity. So it's a regime that you would not access, and the claim is that that's dual to weakly coupled quantum field theory. So it's and I will give you the dictionary in the next slide. So this is what makes it one of the things that makes it very remarkable. I must also stress one aspect, that it's a quantum equivalence of the Hilbert spaces on both sides. So this dictionary translates the quantum mechanical, it's an equivalence between two quantum mechanical systems, even though it may be framed in different ways, one as a quantum field theory, the other as a theory of quantum gravity. But in the end, they're both quantum mechanical systems, and the Hilbert spaces, they are isomorphic. I mean, they are equivalent in the sense that the eigenstates of the Hamiltonian on one side are exactly the eigenstates of what you would call the time translational generator on the bulk side as well. So there's a dictionary which translates between operators on the boundary theory and states in the bulk theory. So I will use always the boundary for this d-dimensional field theory and the bulk for the d+1 dimensional gravity theory. In fact, you can translate the dimensions, or more precisely the anomalous dimensions, because you are considering in general an interacting quantum field theory. So the dimensions of operators will not be those of their canonical free field dimensions. They will have a non-trivial, they will be typically a non-trivial function of the coupling. And that dimension of these operators corresponds to the energy eigenvalues of the corresponding states in the bulk in this dictionary. So the operators here and the states here, the dimensions are mapping to energies. So these are some elements of the dictionary that I'm trying to tell you here. Similarly, if you wish, this refers to the 2-point functions of the field theory. You can look at the 3-point correlators, and those are capturing cubic interactions in the bulk theory, where you have a gravity and a tower of particles interacting with the in the bulk. And so now let me tell you this dictionary, which explains my statement in the previous. So I'm trying to make a little more precise the statement I made in my previous transparency. So let me take you through that. Now, in these large N gauge theories, you can define something called the 't Hooft coupling, a lambda, which is essentially the Yang-Mills coupling square times the rank N of the gauge group. This is the combination that you hold fixed as you take the large N limit, and as 't Hooft pointed out first, and this is why it named. And this quantity, which is one of the parameters of the field theory, translates into the radius of the anti-de Sitter spacetime. So R is just the radius. It's not the curvature. It's just the radius. And the radius is in fact related to this lambda by something in the simplest case of 4-dimensional field theories and 5-dimensional anti-de Sitter. The radius is a lambda to a power, like 1/4, a positive power. And this is why I made the statement that a strongly interacting lambda, so when lambda is very large, then the radius is very large, therefore the curvature, which is the inverse of the radius, is very small. And that's why you can trust Einstein's gravity in that limit, where the radius is so large that it's kind of very weakly curved, and you can think of small long wavelength description, which is what the Einstein theory is. And conversely, if the coupling were very small, where you would access it perturbatively in the field theory, that corresponds to the radius being very small, which is the curvature being very large. So it's the opposite regime. And this is why the statement I mentioned earlier of this duality. So there's one more parameter that you normally have in a large N gauge theory. In fact, the reason it was introduced by 't Hooft is that you can take 1/n as a parameter, and in fact, that as observed by 't Hooft, organizes the Feynman diagrams in terms of their genus, very much like a string theory does. And in fact, here you have a precise dictionary that 1/n is effectively translates into the string coupling that I had in my slide on string theory. This is what was proportional to square root of the Newton's constant. G string square was Newton's constant. So G string this G subscript S is related to 1 over n by a factor of lambda, essentially. So when n is very large, that means GS is very small, and that's why the large n expansion is a perturbative expansion of the string theory. Note that perturbative expansion of the string theory is not the same as the perturbative expansion of the gauge theory. The parameter which controls the perturbation expansion in the bulk is 1 over n or GS, whereas the thing that controls the perturbation expansion in the boundary is lambda, or the 't Hooft coupling. So they are very different in this large n limit. This is sometimes a cause of confusion, and this is why this is a very interesting duality. There are two different kinds of perturbative expansions here, and the interplay between them allows you to kind of get a lot of mileage. So this is what is called the string coupling. And this is the statement I mentioned earlier, that very strongly interacting quantum field theory, the radius is very large, and you can describe it by low curvature Einstein gravity. When you consider a weakly interacting quantum field theory, then the radius is very small by this sort of equivalence here. That's a highly curved or stringy geometry. So okay, so I told you some things about this ADS safety. So why is it a big deal? Perhaps looks interesting, but I want to tell you there's a lot more to this. Firstly, from the gravity side, or the general relativity side, it gives a very concrete model for what a quantum gravity description can look like, at least for this class of spacetimes. So it's already, even if anti-de Sitter spacetimes are not the spacetimes we live in, or very far from the spacetimes we live in, but nevertheless, in the challenge of understanding features of quantum gravity, even having one class of spacetimes, a fairly realistic class of spacetimes, which where you know what the quantum mechanical description, microscopic description of the gravity theory should be, that's a big advance. And we see that at least here, there is this idea of holography that's concretely realized, that d-dimensional boundary theory is a microscopic description, gives a quantum mechanical microscopic description of the bulk theory. You can put the boundary theory on a lattice or whatever, discretize it, and make a well-defined quantum mechanical system. So it's as well-defined as a quantum field theory is. And these are, so these microscopic degrees of freedom are on a kind of a screen at the boundary, and it's in terms of these familiar quantum field theories. So that's the positive thing from the point of view of gravity. From the point of view of quantum field theory, this gives a very remarkable and, I think, unsuspected description of strongly interacting gauge theories in terms of gravitational physics. This is what I said earlier, that when lambda is very, very large, you can describe it in terms of just Einstein gravity. So you're solving Einstein's equations to learn about a highly quantum regime of the gauge theory. To me, one of the things I think that makes it very compelling is that I think it really realizes an old idea going back more than probably about 150 years from Faraday and Maxwell, that flux lines of gauge theories are really string-like objects. And I will say a bit about this at the end. This is something that people like Faraday and Maxwell, of course, had tried to, in fact, formulate electrodynamics in terms of the lines of flux rather than the electric and magnetic fields. And in some sense, we are seeing a realization of that in a true sense, or in a more tractable sense, in the context of gauge theories and quantum gauge theories. So it's an idea that has been, I think, means been in the minds of many people in the last 150 years. But I think there's a very concrete realization. For people who are maybe here from, I don't know, some people from a more mathematics background, I think it's sort of comparable in its flavor and scope and grandeur to the Langland's correspondence in mathematics. So apart from mathematics, actually, where ADS safety has also had some impact, it has also made an impression in many areas of theoretical physics. So to just list a few, in high energy physics, it has led to new scenarios like the Randall syndrome scenario for physics beyond the standard model. It has led on a different direction to sort of new ways of thinking about scattering amplitudes of gauge theories, and new ansatz like the Byrne-Dixon Smirnov kind of ansatzes for scattering amplitudes in gauge theories, which are very important for calculating radiative corrections in gauge theories for CERN, for instance. It has had an impact in QCD through kind of toy models of QCD, what are called ADS QCD. These are effective field theories, but I think they kind of give you a way to capture QCD or model QCD, some of the strong coupling effects, the bound states of QCD, in a way which is kind of complementary to what you do on the lattice. It has also had an impact in studies of QCD at finite temperature, like the quark gluon plasma. People might have heard about the viscosity of these strongly interacting systems and the relation to the quark gluon plasma, etc. Cosmology, it has given rise to many scenarios, swampland and other explorations recently, condensed matter physics, various ADS-CMTs, and recent developments with this SYK model, quantum information through the Ryu Takayanagi and HRT formulas. So I won't touch on all these things, but just to show that these are very, this has been a very fertile source for many areas. But now let me try to tell you a little bit more about this program that I've been developing to try to derive this correspondence from first principles in some sense. So it's often kind of put out there almost like a miracle, or a kind of just a as if some oracle had just told us there is this equivalence, and you can do many things. You can check, you can verify, you can be amazed at how these two sides are equal. But I think as a physicist or a scientist, you want to really understand the underlying mechanism. When you see some non-trivial equivalence like this happening, you want to understand what is it that makes it tick, or more a little to sharpen it, how exactly do large N quantum field theories reorganize themselves into a theories of strings? So I will try to address that question, which in a sense goes back 50 years. So the insight that Maldacena had about 25 years ago, which led to this more precise ADS-CFT correspondence, uses objects called D-branes in string theory and something called open-closed string duality. So when I showed you that picture about the strings, I really drew only closed strings, which are like rubber bands, and which trace a world sheet which has no holes in it apart from the boundaries. But you can have another set of strings which are more like just a piece of string with two endpoints. And that, when it traces a world sheet, is a sheet which now has a boundary in addition to, I mean, it has a boundary which is the two edges of the string that tracing out. So those are those are world sheets with boundaries, or Riemann surfaces with boundaries, whereas the closed strings are typically Riemann surfaces not quite with boundaries. If you think about the asymptotic states, they are more like punctures, and so you can so the closed surfaces are closed strings. The surfaces with boundaries are open strings. Yeah, I think Shravan, you have a
Yeah, I felt like to ask the question here.
Yes.
When you mentioned this open-closed string duality, so is it related to this double copy, so that you have gravity amplitudes as square of angle?
A square? No, that is slightly different. I mean, it's not quite the same. I mean, there's some kind of it's not. The short answer is not the same. This is a kind of a way in which the Yang-Mills theory itself, and not two copies of it, but the Yang-Mills theory itself is dually described by our string theory. So maybe yeah. So whereas in the other one, it's more a kind of a mathematical equivalence of the fact that if you glue two open string theories together, you get a closed string. Here also, we will be kind of gluing together the open strings, but they will be glued to themselves and kind of, so it's not two copies, but it's sort of one copy in a sense.
And one more short question. So this duality, how it is related to the, I mean, ADS-CFT, the holography. So this is, I'm missing the connection, because this duality, as I understand it, is, sorry.
Yeah. So no, I'm glad you asked. This duality is a more general version of the ADS-CFT duality. ADS-CFT is a very specific case of this duality that so open-closed string duality. So I will. This is what I was going to explain. That what Maldacena understood was that open-closed string duality is, in a sense, underlying the gauge string duality or ADS-CFT correspondence, and this is the idea that you can view the large N gauge theory Feynman diagrams as really open string diagrams. You can think of them in a way which I will show in future slides, that you can think of actually when I mentioned that an closed string has graviton as its simplest excitation, I should have also told you that an open string with these two endpoints has a Yang-Mills-like gluon as its lowest excitation. So open string theories naturally contain gauge theories, and that's the underlying reason for what you said about this double copy. But here we are only just consider a single open string theory, and they capture in some low energy limit, they capture large N. I mean, you can take the N to be anything, it's arbitrary. You can take a large N limit. And so the large N gauge theory diagrams can be viewed as open string diagrams. And I'll have a picture in a later slide. And so the open string diagrams, I've just drawn a cartoon here. This is an example of an open string diagram because it has boundaries. This is an example, the right side, is an example of something without boundaries. And so that's a closed string. And somehow this mysterious open-closed duality, you can translate Maldasena's statement into a statement that in some ways, if you sum over all the holes of this theory, you get closed string theory. And that was the original understanding. This is not what I will actually, I'll have a slightly different take on this, but in that case, the way Maldacena argued, which was basically using two different pictures of the same object, D-branes, in string theory, he arrived at the ADS-CFT correspondence by kind of thinking of D-branes as on the one hand, sources for gravity, and therefore they change the space-time and becomes like anti de Sitter space-time. On the other hand, you can think of D-branes as sort of objects on which open strings end, and therefore can be described, whose excitations can be described by gauge theories, open string excitations or gauge theories in some limit. And since these are really the same thing, the same object in string theory, you say that somehow when you sum up all the open strings of the D-branes, it effectively becomes a closed string theory. So that was the kind of philosophy or the underlying argument. But this is very difficult to see when you are doing when you are working at large coupling, which is how he originally arrived at it, using the Einstein gravity description of d-branes. So it's difficult to see this happen at a large G-string. So what I will do is instead go to small lambda, which is something we understand perturbatively in the gauge theory. So that's how I will be trying to arrive at this ADS-CFT, try to derive it in some sense. But first, let me say some words about the why it's important to derive it. I think I said earlier also, but it's very important to understand why this duality works. And even from very practical point of view, people actually know only a small corner have mostly explored a small corner where the coupling is very, very large. So in a sense, the stringy version of the ADS-CFT going beyond Einstein's theory is still relatively unexplored territory. And the couplings are where the couplings are of order 1, but even in the limit where the strings are only classically interacting, or the string perturbation expansion is small, there's still it's still not very much explored. And this is the regime where you might be actually wanting to understand QCD or some other strongly correlated system. The couplings are very large. What kind of dual string theory do you have? So, and besides, you would like to understand, if I give you a general large N gauge theory, let's say, can we understand if it will reassemble itself into a string theory? Is it equivalent to a string theory always, some of the times? In which cases is it equivalent? So we should have a first principle way of going beyond many of the examples which often rely on supersymmetry, though there are many non-supersymmetric examples as well. But supersymmetry is a very convenient tool, and it allows you to say many things. So, but obviously there are many more quantum field theories than there are supersymmetric theories, and you want to understand, is this phenomenon true for all of these theories as well? So you want to be able to do that, and that's one of the things I think a good way of deriving it will let you know, will tell you. Also, this holography, you would like to demystify it from the bulk point of view. You could ask the question, how does a quantum space-time emerge from a large N gauge theory? Because a large N gauge theory is just a gauge theory. How does it encode a higher dimensional space-time in it, the quantum level? And that may help us to understand whether this phenomenon is true for flat space quantum gravity, or perhaps de Sitter space, etc. So, as I said, most work has been in this Einstein gravity limit. So I like to draw it by this cartoon here, where you have basically the same parameter space that I mentioned to you earlier. I'm drawing it along two axes. So along the horizontal axis is this lambda, or this coupling, the 't Hooft coupling, which, as I said, is proportional, or some power of this is proportional to the radius, measured in some string units, in the string length or the string tension. So that's the horizontal axis, with this being lambda being small. So that's perturbative quantum field theory. This is where the radius is very large, or lambda is very large. And that's where, as I said, classical gravity is valid. So these are the two regimes I talked about earlier. This is accessible from the quantum field theory side. This is accessible from the gravity side. And then there's the vertical axis, which I didn't, and I won't describe very much here. And that's where you have the string coupling perturbation expansion, that is G string. And this is, you can increase G string here, or equivalently 1 over n, because they are related. So this is sort of the n equals to infinity limit, and you're making n finite. And this is a more quantum string regime. But this regime itself, where you treat n very large, you keep n always very large, but you vary lambda, this coupling, the Yang-Mills coupling, as you vary this, can you kind of follow the theory all along this limit? As I said, most work has been in this limit, where it is, of course, Einstein theory, you can extractable, and you learn many things about very strongly coupled quantum field theories from this limit. But I want to shift the focus to this corner, or this lamppost, where we understand the field theory, but we don't understand the bulk, because again, to repeat, the radius is proportional to lambda to a positive power. So lambda small meaning the radius is large, or it's very highly curved. Equivalently, you can think of it as a tensionless limit, because you can think of holding the radius fixed and taking the string tension to 0, or 1 over this LS parameter here to 0. So this is a highly stringy regime, and because you're far from any Einstein gravity, but you're still classical from the point of view of the bulk, because that is governed by this parameter, and we are sticking to the classical limit here. N goes to infinity, or G string goes to 0. We can treat it perturbatively. Okay. Now, I want to sharpen a statement of what constitutes a derivation. I told you there was a dictionary, and the dictionary related dictionary firstly relates states and operators between the boundary theory and the bulk theory. And so you can forget about some of the labels here. Just you need to think of this O as an operator in the gauge theory, some gauge invariant operator, actually a single trace. That's just a technical, that's a simplification. You can consider these gauge invariant operators, which have some quantum numbers. So those are these extra labels. They're labeled by some position X on the boundary. And they are dual to operators or states in the bulk created by in the language of the string theory. These are represented by so-called vertex operators in the worldsheet theory, which are labeled therefore by a position on the worldsheet. So Z is a position on the worldsheet, and X is a label of the target space, the boundary theory that we have, and carrying the same quantum numbers. In fact, H will be the dimension of the conformal dimension of the operator. So for me, a derivation is a way to kind of, the ADS-CFT dictionary tells you that you consider an endpoint function of these operators, which can be very different operators at different points, x1 to xn, on the boundary. I'm taking now the Euclidean theory, so the boundary is a sphere. And I look at this correlator and I pick out its genus G part in the 't Hooft expansion, in the 1 over n expansion. That's the power, the n to the 2 minus 2g piece. So G equal to 0 is where we would mostly work on at. That's the genus 0, or the sphere topology of Feynman diagrams. And that is the leading piece. You can see that's the piece that goes like n squared. But you can do it for any fixed genus. You pick out that contribution of the genus expansion of the correlator on the left-hand side. And the claim is that it is equal to a correlator on the right-hand side of the string theory, which captures the bulks correlator. And what is that object in the dual string theory? It's a correlation function of a two-dimensional conformal field theory that lives on the worldsheet of the string. That's the way in which you define the it's like the first quantized description of a particle you'd write in terms of a world line quantum field theory. Here you describe in terms of a worldsheet quantum field theory, which turns out to be a two-dimensional CFT. You shouldn't confuse this CFT with the space-time CFT. So this two-dimensional conformal field theory, you compute a certain correlator of these operators on a genus G Riemann surface with these n punctures. That's what the sigma Gn refers to, a genus G Riemann surface. That's the world sheet with these n punctures, which are these external operators for this correlator. And your instructed string theory tells you that you have to sum over all the possible world sheets of that topology. So this is what mathematicians call the moduli space of Riemann surfaces of genus G with n punctures. It's a well-defined mathematical space, and this is basically realizing the Feynman prescription that you have to sum over all possible world lines, world sheets. So in this case, all the possible Riemann surfaces, which are therefore parameterized by this moduli space. Both sides of this, so I want to say that a derivation is when you can show the equality of both sides, because both sides have well-defined independently. On one side, you have the left-hand side, you can think of so quantum field theory is well-defined in many ways. I mean, you can put it on a lattice or whatever. The right-hand side is similarly, it's a question in a two-dimensional conformal field theory, a sigma model, which is also in principle well-defined. So the equality is a very surprising mathematical equality. It's a mathematically well-posed question to ask, are these two things equal? They are independently defined. They are very autonomous systems. There's no reason for an equality. In fact, I want to be able to just do more than show an equality. I want to make that equality manifest. Can I make the correspondence a tautology, kind of make it obvious that the right-hand side is the same as the left-hand side? Because if it's true for all operators, all quantum numbers, for all x1, xn, and for all n, for all g, this is as you can imagine, it's an infinite set of equalities. And the only reason for that to be true would be if there's some hidden way of showing their all underlying equivalence. So of course, this is a tall thing to do, but as I said, it is potentially tractable if we start with the left-hand side in the perturbative limit, because we know the perturbative field theories are given in terms of Feynman diagrams, etc., and we try to reconstruct the right-hand side of the dual string theory. And this is and if you might think that, oh, the free field limit or perturbative, this must be trivial because we are so used to it. I want to just give you a caution that there are still many surprising things from both sides, actually, in this limit, which are quite surprising. In fact, from the string theory point of view, this tensionless limit may be a very special point. It has a large unbroken symmetry, a higher spin symmetry. There's a topological, there are many speculations about it corresponding to a topological phase of gravity, where, and when you go away from lambda goes to zero, this big symmetry is Higgsed, etc. So that's a very interesting thing from the bulk point of view, from the string point of view. But even perturbative Yang-Mills, we seem to continue to discover new structures, new things in scattering amplitudes, various things that maybe some of you are familiar with. This is what I want to tell you, is that this lambda goes to zero is a non-trivial limit even in the gauge theory. So the basic idea behind this is to sum over all the world line topologies on the Feynman diagrams on the large N theory, which is a large N matrix theory or a large N gauge theory, and show that this sum, so the equality is a statement of the sum over these world line topologies being equal to a sum over these world sheets, or these integral over this moduli space, as I said. But we will actually try to say that the sum is the same as this sum on the right, and they kind of it is true kind of term by term that there will be an equality, kind of making a stronger statement about how these two state sides can be equal, and that this can come after gluing up the double lines. So the slogan, in a sense, is that each Feynman graph of a perturbative quantum field theory corresponds to a particular world sheet, a particular point on the moduli space of the string world sheets. So this is a kind of a refinement of 't Hooft, who associated a genus to these double line Feynman diagrams. So I didn't probably say what these double lines are. So you can, in these Feynman diagrams in a large N gauge theory, the propagators are gluons, which are matrix valued, and therefore you can think of representing them, as 't Hooft did, by a double line with each index, each kind of a fundamental index of the gauge theory being carried by one of the two lines. So the adjoint representation is carried by this carries this two indices, and it's a very convenient way to keep track of the diagrams. But also, I think physically it is the right idea, because it's these double lines which are this which you can think of as strips, which are these open strings I mentioned earlier. So this is the picture I was promising of an open string. If I just focus on one of these strips here, which I can think of as one of these lines of this Feynman diagram. And here I've drawn three strips. So there are three different Feynman propagators. And the statement is that you can glue each Feynman diagram in a very unique way to give you a closed string. So this is the sense in which I was saying that it's not a double copy, it's the single copy. The single Feynman diagrams of this theory give you a closed string world sheet. And this utilizes a certain mathematical parametrization of the moduli space, which allows you to show that you can kind of map these two sides. And this is the so-called Strebel parametrization, which, so I...
Sorry, I have a question. Sorry.
Yes.
Do you think that entanglement plays some role in this gluing, in the sense of the van Ransdonk argument that I could think in that string at the microscopic level can arise or emerge from some kind of entanglement in this context?
Yes, I think there's something very much like that happening. I won't have time to say it in this talk, but one of the pictures that emerges from what we have been doing is that of a kind of a string bit, that these strings, that you can think of even the Feynman diagrams, each of these are kind of individual string bits, and you're gluing up these string bits to form the closed string. So each string bit is really like a qubit in some sense. It's like the spin chain picture that people had of Yang-Mills operators. And so those are the individual qubits, and they are kind of building up the string. And so I think there is a relation. It has not been fleshed out, but I think morally that what you're saying is correct.
Thank you.
So the picture, and I can only draw the picture right now, I mean, and point you to some of the papers, that these ribbon graphs or these double line graphs of Feynman diagrams, you can kind of glue these together to form these quadrilaterals. So you can think of all these strips as effectively conformally mapped to this quadrilateral, these strips to this, and these to this, etc. So each of these are color-coded. And this is a way to kind of then create a Riemann surface in a very unique way, which is fixed by the numbers of these Wick contractions, or these lines over here. These lines are essentially Wick contractions that you normally do in your perturbative quantum field theory. And there's a very precise way to make this equivalence here to go to a particular Riemann surface and with particular punctures. So you can kind of think of this as becoming like a 4-punctured Riemann surface. And these are some kind of, if you wish, some kind of a foliation of that Riemann surface. Yeah, so I don't, in the interest of time, I will not talk about the mathematics of this. There is the beautiful theory called through the Strebel graphs, and which was exploited by Kontsevich and Hare, Penner, etc. So let me very quickly just maybe I don't have the time to go into the details, but that there is a proof of concept in that this program kind of really works, and that is in the context of the tensionless limit of 3-dimensional anti-de Sitter theory and 2-dimensional CFT, and a similar 5-dimensional anti-de Sitter and a 4-dimensional CFT. So in fact, in the case of the ADS3 case, it's one of the old examples of the Maldacena paper of a string theory on ADS3 times S3 times T4. But when you look at a very specific case where it's sort of with 1 unit of flux through this ADS3 or S3 special NSNS flux, then we made the conjecture or the claim that it is a dual to 2-dimensional CFT, the so-called symmetric orbifold CFT of n copies of T4, the same T4, mod out by the symmetric group that permutes the n copies as n goes to infinity. And in fact, we could check that the spectrum agrees. We then also could show that these correlators of this kind are manifestly the same. And we have begun to do that for the case of free n equals to 4 super Yang-Mills, which was the supersymmetric Yang-Mills theory, which was at the heart of the canonical example of the ADS CFT. And in the dual CFT, in both cases, we've proposed matching of the spectrum. We find a matching of the spectrum in the n equals to 4 Yang-Mills case, but in that case, we have still to flesh out the dual string theory somewhat more explicitly. Yeah, so I think I will, there's many things I think I have to skip now. I think it was too optimistic about the things I would do, but there are many interesting connections to the twister strings, and it seems to come together in a very general way, that these are not isolated examples, but there are sort of a very general underlying principle behind this duality. So just to maybe summarize and conclude, I think deriving gauge string duality can really overhaul our understanding both of quantum field theory and quantum gravity. And there are text cases, I didn't go into that, but I mentioned these in the tensionless limit, that's the lambda goes to 0 limit of in both ADS3 CFT2 and ADS5 CFT4, where this general program has begun to be explicitly carried out. You could close the circles. I mostly emphasize going from the fields to the strings, but you can in many cases talk about the string theory worldsheet and go back to the field theory as well. And this is I mentioned this discrete string bits picture that seems to come out in the dual worldsheet theory. We have recently also generalized this to simple matrix integrals, which is the simplest kind of quantum field theory. And you can go away from the lambda goes to 0 limit as well. And we have been doing that recently also with Matthias Gaberdiel. A lot of this work was with Matthias Gaberdiel in recent years, and other collaborators like Lawrence Eberhardt, and recently with Matthias and his student Beat Naers, we have gone away from the tensionless limit in a particular controlled, in a certain controlled expansion. I again didn't have time to tell you about the role of these twistor string theories that underlies it, but seems to suggest an underlying topological string. And then there is, I think, a deeper mathematical a role also, including a kind of a role for arithmetic or kind of number fields in this gate string duality through this so-called the Treble dictionary, which again I didn't have time, but I just want to throw it out there as some tantalizing ways in which I think this can connect to other things. Finally, let me just close with a quote from Paul Dirac from 1955. This is before any string theory was proposed. It's a set of lectures he gave in Bombay in India, and he was trying to again struggle with this idea of creating a different description for electrodynamics in terms of the lines of force. And he wanted to think of an electron as the end of a single Faraday line of force, and the electric field in this picture are discrete Faraday lines of force, which are to be treated as physical things like strings. And then he says one then has to develop a dynamics for such a string-like structure and quantize it. And in such a theory, a bare electron would be inconceivable, since one cannot imagine the end of a piece of string without having the string. So this is, for me, I think a lot of the motivation to understand string theory is the fact that it really arises very naturally from quantum field theories, like in some ways the generalizations of electrodynamics. I think Dirac's attempts and those of Faraday and Maxwell were kind of doomed because they were looking at classical, or even in the case of quantum electrodynamics, for U1 theories, it's more difficult to see these effects, but they come out much more naturally in a UN theory in the large N limit. And that's, I think, where we are kind of beginning to see this very general phenomenon. So thank you very much.
Okay, thank you for your very interesting talk. Questions, please. Yes, Shravan, please ask your question.
Hi, Rajesh. Thanks
Yeah.
for the very inspiring talk. And I have 3 questions. So,
Okay, very good.
well, starting with basically when you explained the space-times asymptotically ADS. So, well, what is when interesting is, like, for example, with the recent developments of understanding black holes in string theory. So, for example, if you take asymptotically Minkowski spacetimes, like, for example, short-shell black hole, there is a interesting role the BMS symmetries play, because
Yes,
this has been, I think the subject is evolving now, and
yes.
also due to the understanding of shock back reaction of shock waves when the particles move in this in a curved spacetime. I'm just curious, from the concept of ADS-CFT, like we have, I mean, there is a correspondence, boundary, and bulk, but we always have interest to know what is happening in the bulk, and
Yeah.
what could be the role of analog of BMS symmetries in the ADS would play in understanding the physics of the bulk. That's one question.
Right. So shall I answer that before you go
Yeah.
to the other, or do you like to ask all your questions? If
No, I think the other question is entirely different. Maybe if you can answer this question.
Indeed, how does this generalize in a way to asymptotically Minkowskian spacetimes, and in particular the role of the BMS group? I think this is being actively explored. There are at least 2 different kinds of approaches people have been taking. One is what is called celestial holography, where people have been trying to rewrite the flat space scattering amplitudes in asymptotically Minkowski spacetime in the language of a 2-dimensional CFT. So not 3-dimensional. So let's say we are in 4-dimensional Minkowski spacetime. The celestial holography program tries to write the scattering amplitudes in in terms of those of a two-dimensional CFT, which they would like to think of as living on the celestial sphere at Scry Plus at a particular at any point in Scry Plus. So it's a kind of a even more drastic holography in the sense that you're going from D to D minus 2 dimensions. You go not only to Scry Plus, you go to a specific point in Scry Plus. But then there's another approach which is what is more directly connected to the BMS symmetries. So here also the BMS symmetries play a role, and but there's another approach where BMS symmetries, I think, arise also where people are trying to look at some kind of holography on Scry Plus. But Scry Plus is a null direction, and so it's a little degenerate. So to define the theory there, and there is the so-called Carolian symmetry, which is really like or conformal Carroll symmetry, which is like a BMS symmetry. And that is another kind of an approach that people have. And I think these are interesting approaches, and people are trying to rewrite the scattering amplitudes to bring out their structure in terms of either this two-dimensional CFT, and many aspects of the scattering amplitudes are very transparent in this two-dimensional language, or like the soft theorems and so on. So yeah, so that's one approach. But we still don't have, I think it is still evolving. So there are these two ways, but BMS symmetry plays an important role in both of them.
Okay, thank you. And my another question is a bit different direction. So basically, as you mentioned, that open string duality is much more general than the ADS CFT. So I'm curious about understanding of the duality in de Sitter space. So of course, there are some techniques which people are developing in the sense of calculating cosmological correlators with the bootstrap techniques, which are kind of inspired from several techniques developed in ADS-CFT. But my question is specifically about duality. Is it possible to see this duality in de Sitter space, and are there any attempts made?
I think the de Sitter space is even more confusing than flat space, or they're both. There are proposals again, and people look at because de Sitter has a kind of a space-like boundary rather than a time-like boundary, and so how do you translate observables in de Sitter? There's a de Sitter CFT kind of correspondence. How do you translate observables? And there are proposals, but still no, I think, satisfactory microscopic description that we know.
Okay, thank you. And my third question is related to, again, is the duality is a feature of in general? I mean, for example, in string theory, there is a vacuum problem. There are many vacuums, the landscape problem. But does this duality make some selection of vacuums? I mean, does it work only in particular vacuums, not in the other?
So here we are looking at a class of vacua, which are these asymptotically ADS vacua, and there are many of those. I think the space is even larger, because my general feeling is that many more quantum field theories, and not just some supersymmetric quantum field theories, many more quantum field theories will have their duals in terms of space-times which may be asymptotically anti-de Sitter, but may not be supersymmetric, etc. And there's a whole space of string vacua which I think have not been explored, which would be dual to large N quantum field theories in general, like the large N quantum field theory dual to QCD. But I think we have not explored those. So in a way, what I'm saying is that there's even more. It certainly does not solve the vacuum, this problem of many vacua. In fact, I think it is a feature of the theory that there are so many different vacua, and I think you need them to correspond to all the different kinds of quantum field theories that are there. But again, what what you said in your earlier questions. There are also flat space vacua and maybe approximately de Sitter vacua. And we don't have a good description of those in terms of holography right now. But perhaps one day after, if we understand the ADS case in detail, in a microscopic way, then we may hopefully make progress on that. But that's just a hope.
Okay, thank you.
Okay, I saw previously that Richard Kerner
Yes,
would
yes,
like
yes.
to ask the
Yeah,
question.
I
Do
have
you
another
mind
question.
to-
Yeah,
Yes.
if
Okay.
if an electron is the end of the string, what is on the other end?
Well, it depends. I mean, you can consider electron-positron pair. That's the thing that is in some sense gauge invariant. An electron by itself is not a gauge invariant particle. It's like in the quarks. You need to have a quark and an antiquark. So, of course, when we normally study, we talk about electrons and we talk about electrons in the lab and so on. But the gauge invariant operator is really the electron with a Wilson line string, which is stretched to infinity.
Not to infinity, okay. And there is
Yeah.
nothing there.
Yeah, so that's really the gauge invariant quantity, and that's why Dirac is saying what he is saying, that you have to have that string at the end. You can't just have the electron.
Like with the monopole, the same.
Yeah.
Okay,
That's
thank you.
Okay, I see one more questions. I see Hong Wu. Please ask Hong. Please ask your question.
First, thanks for your very interesting talk. I have a question. What is the Nobel role for Twister worship theory in this? What is Nobel role for Twister string theory?
For twistor string theory,
Yeah.
what is the role? The dual world sheet description in the tensionless cases that I mentioned, they seem to be most in the tensionless limit, seems to be most naturally described in terms of the twistor target space. So the world sheet variables are twistor fields, which take values in the twistor space of, say, ADS5 times S5. Rather than think of string theory directly moving, having a target space ADS5 times S5, I think it's some more natural to maybe think of it having target space, the twistor space corresponding to ADS5 times S5. At least that is the proposal we are making, and we are trying to trying to make more precise. So that is the role that we currently see.
Okay.
More questions, please?
I have a question, Irina.
Hello.
Hello, hi. Sorry, I didn't raise my hand, but yeah.
Okay, Ruka, please.
Yeah. Thank you very much for your talk. I have a question. I'm not familiar with the IDSFT, so thanks for this nice review of dualities and IDSFT. So my question is more like, I really like this way of thinking of IDSFT as a tool, basically. Like, even though we don't live in ADS, maybe we can still learn something from this IDSFT correspondence. And since we are most likely living in a four-dimensional space-time, would be nice, at least from my perspective, to understand like some ADS in 4-dimension in terms of a CFT in 3-dimension.
Yes.
And so what is the current status about this? For instance, is there any known 3-dimensional CFT to describe a 4-dimensional ADS bulk?
Yes, there is for 4-dimensional ADS. Again, there is a special supersymmetric case like the ADS5 times S5. This is the so-called ABJM theory. So there is a dual three-dimensional conformal field theory, which consists of a Chern-Simons gauge field coupled to some matter, some specific matter, actually two Chern-Simons gauge groups, SUN times SUN gauge group in special case, or more, you can have slightly more general case, but SUN times SUN in the simplest case at level K, and the other SUN at level minus K, and with some matter fields, which has some supersymmetry. So this theory is dual to the string theory on ADS4 times CP3. That is the simplest case, or more generally, you can think of ADS4 times S7, kind of an M theory. But if you just think in string theory language, ADS4 times CP3. So that is a little more complicated case than the other two that I just mentioned, ADS3 and ADS5. Like you said, you're living in 4 dimensions, but you can choose to have either your bulk in 4 dimensions or ADS4, or you can choose to have your boundary in 4 dimensions, which is the case I was looking at, CFT4. So my motivation is often to consider 4-dimensional quantum field theories or conformal field theories like 4D QCD, and try to ask what is the 5-dimensional bulk description of that. Mm-hmm. So yes, you might be motivated to study physics in 4 dimensions, but it depends on which physics of 4 dimensions are you studying.
In your case, it would be interesting, like, to use 5-dimensional ideas to understand some strong coupling in 4 dimensions without gravity.
4 dimensions, exactly.
Yeah, I see.
Yeah. Okay. Yeah. More questions, please? If there is no more questions, let's thank the speaker again. Thank you very much, Rajesh. Thank you for your brilliant lectures. Yes. Please don't forget to send us your transparencies, okay?
Okay.
Because more interesting part, I guess, is in the end. You skip a little bit. Yes. Okay.
Yeah.
Okay.
Always one has many more things in the slides. Yeah.
Okay.
All right.
Thank you very much.
Bye. Thanks.
Bye-bye.
Bye-bye.
Thank you.
Bye-bye. Thank you.
Thank you.
Bye. Thank you.
Привет, Ира.